So just to recap very quickly, so we mentioned that the pointer is a memory address, and it can be a memory address of an integer, a memory address of a double, or other types as well. And what we have over here, we have two pointers, pointer 1 and pointer 2, and we have two integers as well. So this is the address of an integer, and this is the address of an integer. You can also read it as a pointer to an integer and a pointer to an integer. And then we mentioned that if this is what you have, and you want P1 to point to V1, then you get the address of V1, and this is how you get the address of V1. So this operator over here says, give me the address of V1. And we also mentioned that if you want to dereference a pointer, then you use this notation. So when you see out star P1, you're not printing out the address, but you're printing out the content of that address. Now notice, guys, that this star, it has two different meanings depending on the context. So the context over here is the declaration, but the context over here is an operation. When the declaration, if you have a star in the declaration, it means that this is a pointer. When you have a star outside the declaration, it means that you are dereferencing. Okay? So it has two different meanings according to the context. It's also the same thing for the and sign over here. If you have it inside the function definition or a function declaration, it means that you are passing by reference. If you have it outside the function definition or a function declaration, it means give me the address of. Okay, so again it has two meanings according to the context. Is this a good approach in programming? No, it's not. So you can think of this as one of these I don't want to say problems of C++, but shortfalls, if you wish, one of the concerns of C++. It's never a good idea to have the same operator with two different meanings. Okay. In other programming languages like Java, you'll find that it's a bit more consistent. You don't have such inconsistent definitions. Okay, so we looked at this and we understand it by now. So P1 is equal to the address of V1. You can replace this with V1. So as this is exactly as if you are saying V1 is equal to 42, because you are dereferencing the address, so you're accessing the content. And then we moved all the way up to the new operator, right? And we mentioned that two things will happen with this new operator. What are they? Create an unnamed integer, and then the address of this unnamed integer is assigned to P1. But this unnamed integer, where is it created? Inside the memory? It is created inside the memory, but there is a special location inside the memory for unnamed variables. It's called the heap. It's also known as the free store. So it's known as the heap, can you see it? Or the free store. So the heap or the free store is just a sequence of addresses inside the memory, which will be allocated by C++. We don't know about it, and we don't know where it is inside the memory. We don't need to know. But C++ will use this location inside the memory, which is called the heap or the free store, for dynamic memory allocation, for the variables that do not have a name. So whenever you use the new keyword, the new variable that is created, it's actually created inside the heap or the free store. Okay, not inside the regular memory. Okay. So we mentioned that this creates the nameless variable, and it's stored inside, the address of it is stored inside P1. But it's a nameless variable, how can we access it? We can only access it through dereferencing P1. We cannot access it by any other means. And we also mentioned that this will go inside the heap. Now when we're done with it, we can also initialize it this way, as we mentioned. Let's go back to the example that we wrote. What's this? Solution pointer, so on. Alright, so this is the example we wrote last time, right? So we created a new integer, and we're just assigning, no, we don't need this. We don't need I. So now we're creating a new integer, and let's store something inside it. ptr is equal to 55. Okay, so let's trace this program now. Start without debugging. Start debugging. So look at this point, guys. What's the address stored inside ptr? It's null, right? It's zeros. It's null because we did not execute this statement yet. So what's stored inside ptr is null. Now we're going to create it. Now once it's created, a new integer is created. It does not have a name, but this is its address, and its address is stored inside ptr. Fine. Right. Now ptr does not have a value yet, so this is garbage. So we're going to assign something to it. Here you go. So now ptr has it contains the address. ptr is the address of an unnamed integer, and the value of the unnamed integer is 55. ptr has the address of the unnamed integer, and the value of the unnamed integer is 55. Again, if you go back to the analogy we talked about yesterday, so there is the day before, there is the looker and then there is the key, right? Now the looker itself is the unnamed variable. What's inside it is the number 55. ptr is the key. Okay? No. If you say, let me repeat the analogy. Now the looker is, what's inside the looker is 55. So the looker is the unnamed variable, integer, and ptr is the key. Now if you come and say that key is equal to 55, you change the key. If you change the key, you can no longer open the looker. And we're not interested in changing the key, we're interested in changing what's stored inside the looker. So the only way to do that is through dereferencing. So the analogy is, the unnamed integer is the looker, the content of it is 55, the key is the pointer, which is the address. Okay. We're interested in changing the content, we're not interested in changing the key. You can change the key, but it will no longer open the looker. So how can we change the key? Simply I come and say ptr plus plus. This will move to the next address, right? If I move to the next address, I can no longer open this looker. Maybe I can open something else, but I don't know what it is. Yeah? So keep this analogy in mind, it will help a lot. Fine. Now, throughout the run of the program, and I cannot emphasize this enough, throughout the run of the program, whenever you create a new variable, a dynamic variable, this variable is stored inside the heap, right? Not inside the regular memory. So all the rules that we know about local, global, and block does not apply. This unnamed variable is always there inside the program. So it means that if you create this unnamed variable inside main, and then main calls a function, this variable will not disappear. This function is still there because it's not inside the regular memory, it's inside somewhere else. In other words, whenever you create a dynamic variable, this dynamic variable will live throughout the life cycle of the program. So if you have a function over here called void function1, and let's do this whole thing inside the function, and simply we're just calling function1. Now from what we have learned thus far, we know that any variable that is created inside the function lives between the two curly brackets. Do you remember? Okay, now this does not apply to this unnamed integer. Now there are two variables inside this function. What are they? One variable is ptr, the key, and the other variable is the unnamed integer. The ptr, the key, it lives between those two curly brackets. But the unnamed integer, it's inside the heap, and it will remain inside the heap until either the program finishes or you explicitly delete it. The rule says that whenever you use the keyword in U, eventually you have to use the keyword delete, because the variable, the unnamed integer, is sticky. It will remain there inside the heap until you explicitly delete it. Just like when you open a file, if you don't explicitly close it, it will not close until the program finishes. Let me repeat this again. Inside this function, there are two variables. What are they? PTR, which is the address, and the unnamed integer. PTR, which is the address, it's a local variable, and it lives between those two curly brackets, which means that if we return back to main, PTR no longer exists. However, this unnamed variable, since it's created somewhere else inside the memory, it would remain there. Fine. Maybe you cannot access it. This is a different story, but it's there. In fact, when this function returns to main, there is no way on earth that we can access the unnamed variable, because we lost the key. The key is PTR, and when we returned over here, PTR no longer exists. PTR does not exist because it's a local variable. The PTR is the key. The locker is still there, yet we cannot open it anymore. What this function can do, if you wish, you can make this function return the key. So instead of returning void, the function should return what they think the type is. What's the type of PTR? It's not an integer. It's an address of an integer. So how do I write an address of an integer? No. No. What's wrong with you guys? Integer start. This is the address, right? So this function does not return an integer, does not return a character, does not return hexadecimal. It retains the address of an integer. Okay? But let's declare it as such. Let's make this complete program now. So control copy. This is a function. It creates a variable and it returns it, right? So now I have to have something over here which is of type. Now this is complete, right? Okay. And then I can see out what will be printed out. I have to return. What will be printed out at this point? 55, exactly. And what happened is the following. We call this function, function 1. Function 1 declared the local variable, which is the address key. And when we created an unnamed variable, we accessed the unnamed variable, we opened the locker, and we put 55 in there. Fine. What did we return at the end, 55 or the key? We returned the key. Okay? It would have been different if I do this. What am I returning? I'm not interested in the content, I'm interested in the key. طيب? What I want to pass back to main is the key. So now I'm passing the key. And main over here is receiving the key, which is the address. So now if you have the key or I have the address, you can do whatever you want with it. You can do C in, C out, business as usual. So what will be printed out at this point? 55. Right. Now, this is an indication, guys, that the unnamed integer is still there inside the memory. It wasn't destroyed when we returned from this function. When we returned from this function, PTR was destroyed because it's a local variable. But the unnamed integer, since it's stored inside the heap, it's stored in somewhere else, it will remain there. It's sticky. And I think I repeated this enough times and you got it. Right. So now the question is, well, if it remains there inside the memory, how can we get rid of it? If it's only an integer, 4 bytes, not a big deal. But sometimes you're allocating memory for images if you're writing an image processing program or a video processing program, something advanced. When you allocate memory for images, you're allocating thousands and thousands and thousands of bytes. So whenever you do allocation, you have to do deallocation. So whenever you use the keyword in U, we have to use the keyword delete. So this delete, how does it look like? Well, it's very simple. This is how it looks like. So when we use the keyword in U is the memory allocation, and delete is the memory deallocation. Now when you deallocated the memory, it means that, and let me give you the analogy again. You go to the, where do you get the keys for the lockers downstairs? Do you use the lockers downstairs? From who? Dean? Let's say the associate dean. You can get them from the associate dean. So you go to the associate dean and you get a key for the locker. This is where you got the key for the locker. Okay? So the associate dean says, look, you have locker number 1. Great, it's the first locker. Okay? And then you go to the locker and you store 55 inside it and you close it. Now you return the key, you return that to someone else. You pass the key to someone else. I don't know, maybe you give the key to your friend. Okay? You pass the key to someone else. Your friend is using the locker. Your friend is not using the locker. Now we're going to deallocate. This is the point. When you deallocate, it means that you return the key to the associate dean, and then the associate dean can reuse it for something else. This is the point. Yeah. So when the memory is deallocated, the memory can be used for something else. But if the memory is not deallocated, it cannot be used for anything else. The analogy in this case is the following. You're done using the locker, but you did not return the key. Can anyone else use it? It's a waste, right? And this is what's happening over here. So if you use the keyword in U and you don't use the keyword delete, you're just wasting memory. If you use the keyword delete, then someone else can make use of it. Another variable can make use of it. Yes?
So you're using another pointer here to
Hello, we have 2 pointers, right? One of them was inside the function, and this is a local variable. Once you return from the function, PTR does not exist. خلاص? But what we returned from the function, we returned the address, which is the key, and we stored it in another pointer, okay, in another variable, which is called P. So we have 2 addresses, but PTR no longer exists, because it's a local variable. So now we return the key and it's stored inside P. You do whatever you want with P, and then eventually you delete it. Let's see what happens when you delete P. So let's have a breakpoint over here. Unfortunately, you cannot close the door. Did it compile? Start debugging. Okay. What we did is correct, right? Because we can see the 55 over here. So which means that the content of the locker that you have is 55. And the address is whatever this address is. This is the address that was returned to us from the function. Now let's see what happens when we delete P. When you return the key to the associate dean. That's the analogy. What happened with the content? It's deallocated. So it's like the associate dean will send one of the staff downstairs, they will open the locker and whatever inside there to just clean it out, because someone else will use it, right? So they remove the 55 and they close the thing. Just a minute. There's one thing that you have to notice, is that when you delete P, you don't delete the address, you delete the content. Did you notice that the address remained as is? Can you see it? But what happened with the content? Destroyed. Fine. This address, it's a valid address, but you can no longer use it to access the content of the locker, because you deleted the variable. Now, since this is a valid address, but the content is no longer valid, at this point you cannot use P. So if you try to see out the content of P, let's see what will happen in this case. Now we deleted P, right? And then we're trying to access the content. So let's run the program now. Debug, start debugging. Start without debugging. We printed out P. Start without debugging. This is the 55 over here before deleting, right? Yeah, and this is after deleting. So you can see that after deleting the content is garbage. So the point is, After you use delete, guys, the address is still there, but the content is destroyed. So the solution is just to take this address and say, look, set it back to null, please, because this address, we cannot no longer use it to access the locker, because the locker is now deallocated, it's given to someone else. Okay? So now let's trace it again. Semicolon missing. Start debugging. So now this is the address and this is the content, right? Deallocate. We no longer have access to the content, but the address is still there, right? And to get rid of this address, just set it to null. If you do not set it to null, then you will have a problem which is called the dangling pointer problem. Let me show you what that is in the slides. So we have the allocation. So this is the dangling pointer problem. The dangling pointer problem, guys, it means that you deleted the content, but the address is still valid, right? And you did not set the address to null. If you try to access the content of the address of a variable that you deleted, it will give you unexpected results, and the results are incorrect. So this is called the dangling pointer problem. So the dangling pointer problem is exactly this. You deleted the variable, and still you're trying to access it through the address. Okay, this is called the dangling pointer problem. So whenever you delete a variable, unnamed integer or unnamed double or whatever have you, then make sure that you set the address to null. So Control Z, this is what you should be doing. Okay. Now, in very few cases, if you run out of memory locations, then this new operator might fail. So the new operator will only fail if you run out of locations. So you're trying to allocate memory, but you run out. Okay, so the whole memory is full. There's nothing that can be done. So what will happen is null will be returned. So if you want to check this, you can say that if ptr equals null, so memory allocation failed, cout new failed \n and exit 0. This is how you can check if you run out of memory addresses. This is rarely the case, but it can happen. If you want to illustrate this, maybe we can run this inside the loop, right? So we can say while true, which means run forever. So this is for illustration purposes. We're creating a variable and we're not deleting it, right? And then we're creating another variable and we're not deleting it. And we're creating a third variable and we're not deleting it. If you're patient enough, when you run this and you wait, you'll arrive to a point where the new will fail. So let's see what will happen. Hello, we're inside the loop, right? And we're creating integers and we're not deleting them. What happened? Build solution. Start without debugging. Let's have integer counter, just for the fun of it, and increment this counter inside the loop. So count plus plus, and let's have a breakpoint over here. Build solution, start debugging. So now we're inside the loop, new variables are being created and they're not being deleted. Unhandled exception, bad allocation. We ran out of locations. This is what happened. Bad allocation at memory. So we consumed all the bytes and the program crashed because we were creating integers and we're not deleting them. But we're debugging, right? So if you say continue break, who called this function? If we had exit 0, then it would have been a different story. We would have at least seen that statement. This cout, it didn't print out because we need to print it out to the standard error. If you print it out to the standard error, it will appear. Is it called error? No, the pointers, it's being created, but the cout did not appear. That's all. I think there's C and cout and there is C error. Yeah, but this is what we have over here. If you go back to the slides now for a minute. Good practice to check for null. So test if written by colon u. So just following this, can you see it? But let's run the program one more time now. Build solution, start without debugging. Okay, so we're creating integers and we're not deallocating them. At one point the program will crash. Okay, so you got the point. One last point before you go, and then we will repeat this next time, inshallah. Now let's do a dynamic array. Okay, and we did static arrays. Let's do a dynamic array. So now we're going to have an integer size, and finally we can ask the user for the size. Enter size of array. Come on. Enter size of array and then cn size. And then now let's have an integer star, let's call it array, but this is a dynamic array. And then we can say that array is equal to new int. We saw this before, right? So there's nothing new up to now. But we're not interested in creating one integer. We're interested in creating a list of integers. The syntax to do this is very simple. Just simply do this. If the user enters, for instance, 10, then we're informing C++, I want to create 10 integers, not just one, 10 of them. Don't confuse this with the initialization. If you're doing this, you're creating one integer and you're initializing it to the value 10. But if you're doing this, then you're saying that what I'm creating is an array, and this array contains 10 integers. Okay. Now, this number is not fixed. Luckily, this number we have read it from the user, so we can. Now we have a new array. Luckily, now we can deal with this array as if we are dealing with any regular array. So everything that we have learned about arrays apply in terms of read and write, pass to a function, everything applies. So you can deal with it as if you're dealing with any regular array. Okay? So you can read it inside the loop, you can initialize it inside the loop, you can pass it to a function, you can read it back when it comes from the function, everything applies. So this is what's needed to do the dynamic array, nothing else. We'll look at the details next class inshallah. But before you disappear, I'll just answer your questions.